Welcome to our Quantum Deep Dive. With classical computers, the game has always been about getting smaller and smaller to get faster. But quantum computing? That's a whole different beast. We're talking a complete paradigm shift. And right at the heart of that revolution is the work of a key architect, Andreas Wallraff. Today, we're diving into his story, based on a really insightful essay by Jurgo Schneppet, to see how his work basically laid the foundation for the entire quantum age.
So, here's our roadmap. We're going to follow his journey right from the start, looking at his academic roots and then getting into that massive breakthrough he was part of at Yale. From there, we'll see how he took that incredible success and built a research powerhouse, how his work now literally powers the tech in some of the biggest companies out there, and finally, we'll take a look at the quantum future he helped create.
Right, so it's so important to get this. We are not just talking about making our current computers faster. This is a fundamentally new way to process information. And the building blocks for this new era, they're called superconducting qubits. And they have been absolutely central to Andreas Wallraff's entire career.
So what exactly is a superconducting qubit? Well, the easiest way to think about it is as an artificial atom. It's something we can build from scratch. Unlike a natural atom that just is what it is, we can actually engineer the properties of these. They're built from circuits that conduct electricity with zero resistance, and we can control them with incredible precision using microwaves. That flexibility is a huge advantage, and it's exactly why they're one of the most promising ways to build a real scalable quantum computer.
Of course, breakthroughs like this don't just happen in a vacuum. Wallraff's success was really built on this deliberate, focused academic journey. Every single step gave him a critical piece of the puzzle for what was coming next.
And you can really see the path unfold here, right? It all started with this fascination for that fuzzy line between classical and quantum physics. That led him to his PhD in Munich, where he got his hands dirty and mastered the incredibly difficult skills of low-temperature physics and superconducting circuits. And those exact skills turned out to be the key when he went to Yale for his postdoc, which, as you'll see, is where everything changed. Then he took that massive discovery to ETH Zurich and built one of the world's top quantum labs.
Yeah, that time at Yale, that was the real turning point. Not just for him, but for the whole field. Wallraff joined a team that was aiming for something that sounded almost like science fiction. They wanted to combine two totally different areas of physics, quantum optics and solid-state circuits, in a way no one had ever successfully managed before.
The goal itself sounds almost poetic, but the physics behind it was incredibly complex. The team at Yale, we're talking Wallraff, Robert Schulkopf, and Michel Douveret, they wanted to see if they could get their artificial atom, that superconducting qubit, to have a controlled conversation with a single particle of light, a microwave photon. It was a huge gamble.
And this quest led them to basically invent a whole new field, circuit quantum electrodynamics, or circuit QED. The idea behind it is actually pretty elegant. Just imagine you have this tiny echo chamber, a resonator, and you trap a single microwave photon inside. Then you place your artificial atom, the qubit, right in there with it. Circuit QED is the science of making them talk to each other in a predictable and controllable way.
Okay, so here's how that conversation actually works. First, you trap the photon. Easy enough. Second, you introduce the qubit. Now, step 3 is the secret sauce, achieving what's called strong coupling. This is where the qubit and the photon interact so intensely that they can actually exchange energy back and forth without losing the fragile quantum information. And because of that interaction, the whole echo chamber changes just a tiny bit, which allows you to listen in and measure the state of the qubit. It's just a brilliant way to both control and read out quantum information.
And the impact was immediate. In 2004, the team published the results in the journal Nature, and it was a bombshell. They had actually done it. They achieved strong coupling in a circuit for the first time ever. This paper wasn't just another publication, it was the spark. It was the proof the world needed that yes, superconducting circuits were a totally viable and maybe even the best platform for building a real quantum computer.
So, after a discovery like that, what do you do next? Where do you go from there? For Andreas Wallraff, the answer was to take that breakthrough and build an entire research institution around it. So, in 2006, he packed his bags for ETH Zurich to start that next chapter.
Exactly. He took all that momentum from Yale and founded the Quantum Device Lab. And it didn't take long for it to become one of the most important centers for quantum research in all of Europe, pulling in top talent and just constantly pushing the limits of what these circuits could do.
And at Zurich, Wallraff's focus became really strategic. The lab started tackling the biggest hurdles in the entire field. Things like, how do we make these qubits last longer? How do we design chips with lots of qubits that can all work together? How do we fix the errors that are bound to happen? He wasn't just running experiments anymore, he was literally building the roadmap for the future of the technology.
Okay, and this is where it all comes together. Why does all this fundamental research from a lab at Yale and a lab in Zurich matter to us today? Well, because it is the literal foundation for the quantum computers being built right now by the world's biggest tech companies.
A huge piece of this puzzle is a specific type of qubit called the transmon. It was an evolution of the earlier designs that came out of the Yale group, and its real genius is a design that makes it way less sensitive to all the electrical noise in its environment. And that resilience is absolutely critical for holding on to a fragile quantum state, a property we call coherence.
And the difference this made, it's just night and day. Seriously, the early qubits were so delicate they could only hold their quantum state for a few nanoseconds. But the transmon qubits that Wallraff's lab helped perfect, they are so much more robust. They push those coherence times, how long the qubit is actually useful, into the world of microseconds. That is a massive, massive leap that made the idea of a scalable quantum computer finally feel real. Let's just pause on that number for a second. Over 100 microseconds. To go from nanoseconds to microseconds, that's an improvement of more than 10,000 times. That's the kind of jump that takes something from being a cool science experiment and turns it into the foundational technology for an entire industry.
And that is exactly what happened. The principles of circuit QED and the design of the transmon qubit aren't just ideas in a textbook anymore. They are the core architecture inside the quantum computers being built today by giants like Google, IBM, and Rigetti. The work done in Wallraff's lab basically became the industry's blueprint.
So as we start to wrap this up, it's pretty clear that Wallraff's impact isn't just about one single experiment. It's the whole story, right? From that one fundamental discovery to building a world-class lab and then laying the groundwork for a global industry. It's incredible.
You know, in a way, his career perfectly mirrors the evolution of quantum technology itself. It's the complete journey, starting with a really deep physics question, hey, can we make an artificial atom talk to a photon? And following it all the way to a transformative technology that now has billions of dollars of investment and is attracting the smartest people on the planet.
To put it as simply as possible, as Jörg Oesch-Schneeppert concludes in his essay, Wallraff's work didn't just contribute to the quantum revolution. His work laid the very foundations that it's all being built on today.
And that really leaves us with this final amazing question. With these incredibly powerful tools that pioneers like Andreas Wallraff have given us, what are we going to do with them first? Are we going to design new life-saving drugs? Create revolutionary materials? The possibilities are just vast. So what grand challenge do you think will be the first one to fall?
Thank you so much for joining our Quantum Deep Dive. This explainer was based on an essay by Jörg Oesch-Schneeppert. For more of his fantastic work, you can visit schneeppert.de. Thanks for tuning in. We really hope you'll join us for the next explainer.
Schneeppert.de is a private project by Jörg Oesch-Schneeppert dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.